guessing.
The microphone?
Yeah.
Okay. So the title of this talk is Improved Homomorphism Preservation Theorem from Lower Bounds in Circuit Complexity. And to make the title even longer, I could add, and we also use the new result in graph minor theory. So throwing in the kitchen sink here. So let me give some quick background on the result. So preservation theorems are a family of results in classical model theory that relate syntactic and semantic properties of first-order formulas. So here in one slide are three of the classical preservation theorems known as the Voshtarsky, Linden, and homomorphism preservation theorems. And these were all proved in the 1940s. And what they say are, if a first-order formula phi is preserved under either injective or surjective or all homomorphisms among all structures, if and only if it's equivalent to a first-order formula psi that is existential positive or existential and positive, respectively. Okay. So these are all of these results were originally proved as corollaries of the compactness theorem of first-order logic. So the proofs are non-constructive, and in fact, in the Voshtarsky theorem, the size of the existential formula equivalent to your first-order formula is not bounded by any recursive function in terms of the size of phi. This is something you can show. So finite model theory is a field that was really born in the 1980s. And one of the pioneering papers of Yuri Gurevich, this paper, Toward Logic Tailored for Computational Complexity, asks the question, what's the status of the theorems of classical model theory when you restrict the statements to finite structures? And one prominent failure in this setting is the compactness theorem, which is very clearly becomes false when you restrict its statement to finite structures. Okay, so as you might expect, many of the classical corollaries of the compactness theorem also fail when restricted to finite structures, including the Voshtarsky and Linden's theorems. These were shown in these papers here. So in other words, there exists a first-order formula that's preserved under injective or respectively surjective homomorphisms on the class of finite structures, yet is not equivalent on the class of finite structures to any existential or respectively positive formula. Okay? The result of Itai-Gurevich was in fact shown using an even stronger version, non-uniform circuit version, can be stated actually in this way, that it's a separation between the class of syntactically monotone AC0 circuits and AC0 circuits which compute monotone functions. Okay, so an early result of mine from before I was working in circuit complexity is showing that in contrast to those two theorems, the homomorphism preservation theorem, which sort of lives at the intersection of those two results, turns out to survive when restricted to finite structures. So the result is if a first-order formula is preserved under homomorphisms on finite structures, then it's equivalent on finite structures to an existential positive formula. In fact, the proof here is constructive, and it gives a bound in terms of the quantifier rank of phi of the quantifier rank that you get of the existential positive formula, where there's a blow-up, which is a computable function, so it's constructive, but the upper bound that I get in this proof is a non-elementary function, so it grows faster than any tower of exponentials. In the same paper, I also gave a new proof of the origin of the classical homomorphism preservation theorem, which was constructive and had no blow-up in quantifier rank. Okay, so this I call the equirank homomorphism preservation theorem. So the proof was constructive, compactness-free proof, and in fact, the finite theorem sort of came from looking at this proof and finitizing the construction there. So this is, there's no circuit complexity in this result originally. Okay, so the new result in this paper is a quantitative improvement on the homomorphism preservation theorem on finite structures. So we give a completely new proof of this result that uses lower bounds in circuit complexity and some results in graph minor theory. And we get the same theorem, but now with only a polynomial blow-up in the quantifier rank of the equivalent existential positive formula. Okay, so this is the main result. And this uses lower bound on the AC0 formula size of subgraph isomorphism problem. Okay, so that's the background and the statement of the main result. So in the rest of the talk, let me say a bit about this connection. So I'll start off by telling you what I mean by the subgraph isomorphism problem. then the sort of upper and lower bounds on its AC0 complexity in terms of the AC0 circuit size, which will relate to the tree width of the pattern G, the AC0 formula size, which we can relate to the tree depth of the pattern G, and the connection between AC0 and first order logic, which gives rise to this result. Okay, so here by sub G, so G is always a fixed graph, and sub G is the following problem. So this is the colored G subgraph isomorphism problem. We're given as input a graph X and a coloring of the vertices of X to the vertices of G. And the question is, does X contain a subgraph which is isomorphic to G via the bijection given by the vertex coloring? Okay. This is a much better structured problem than the uncolored subgraph isomorphism problem. And this is a very important family of problems. It includes, as special cases, the k-click problem for fixed click size k. And if your graph G is just a path of length k, then this problem is equivalent to the distance k ST connectivity problem. Okay? So as we can see just by these special cases, that determining the complexity of this family of problems with respect to different computational resources such as time and space would separate complexity classes P from NP, L from NL. So this is a very important and natural family of problems. Okay, and the computational resources that we'll focus on in this talk are the AC0 circuit size and the AC0 formula size. Another nice property of this family of structures, something which is true of the colored version but not the uncolored version, is that the complexity of this problem is monotone with respect to the graph minor relation. Okay, so graph minor is, we say that f is a minor of G if you can obtain f from G by first deleting some edges and vertices of G and then contracting some connected subgraphs of G into vertices. So there's a fairly easy reduction, in fact a linear AC0 reduction, which shows that if f is a minor of G, then there's reduction from the F subgraph isomorphism problem to the G subgraph isomorphism problem. Okay, so what can we say about the AC0 complexity of this problem? So there's some very simple upper bounds which relate the complexity of this problem to natural structural parameters of the graph G. In particular, so it's easy to show that the AC0 circuit size of this problem is upper bounded by n to the tree width of G. And the AC0 formula size is upper bounded by n to the tree depth. So I'll assume that most people are familiar with the concept of tree depth, and I'll talk a little bit more about, tree width, and I'll talk a bit more about the concept of tree depth in the next few slides. Both of these graph parameters are defined in terms of certain kinds of decompositions of a graph. I won't give the definition. Hopefully you've seen this notion of tree width before. So the tree width of any tree is 1. It's a measure of how tree-like a graph is. And the tree width of a click would be k minus 1. And if you're given a width k tree decomposition for G, whatever that means, you can use that as a blueprint to construct an order n to the k plus 1 time algorithm solving this problem. And in fact, you can implement that by an AC0 circuit. Tree depth may be less familiar notion, so let me just define it very quickly. So if T is any tree, okay, rooted tree, then we define the closure of T to be the graph that's formed by adding edges between all ancestor-descendant pairs in the graph T. So this is the closure of a tree T. And tree depth of a graph G is defined as the minimum height of a tree T such that G can be realized as a subgraph of the closure of T. Okay, so this is a nice graph parameter. So this is showing that the tree depth of a click K4 is 4. So it is in fact the closure of just this path. For paths, on the other hand, the tree depth is logarithmic in the length of the path. Okay. And similarly, if I give you a height k tree where G is a subgraph of its closure, from this it's a sort of easy exercise to construct an AC0 formula of size order n to the k, which solves the sub G problem. Okay, so what about lower bounds for this problem? So in previous joint work with Yuan Li and Alexander Razbarov, we showed that for every graph G, the AC0 circuit size is n to the omega tree width over log tree width. So an almost matching lower bound for all patterns G. And a sort of new work, which we use in our homomorphism preservation theorem, the circuit lower bounds that we will rely on, is this result here, that the AC0 formula size of this problem is related to the tree depth. So it's n to some polynomial in the tree depth. Okay? These are both generalizations of sort of special cases. This lower bound was first proved for the k-clique, and this for distance k connectivity. So you can see these as generalizations to arbitrary pattern graphs. Via connection, which I'll describe in a bit later, so these circuit size lower bounds imply lower bounds on the descriptive complexity, the first order, the complexity of first order formulas which define these problems. In particular, AC0 circuit size is related to the variable width of this problem. So any first order formula which is defining this problem has to have a subformula with at least the tree with many variables. And similarly, quantifier rank is related to tree depth. And these each have kind of corollaries which resolve with open problems in finite model theory. This result here showed that the so-called variable hierarchy of first order logic is strict on ordered graphs. And this result here gives our polyrank homomorphism preservation theorem on finite structures. Okay, so that's a mouthful. So the other ingredient which goes into this result is a new result in graph minor theory. So recall that the complexity of the subgraph isomorphism problem is minor monotone. So if f's a minor of G, then there's a reduction from sub f to sub G. These two important parameters, tree width and tree depth, are both minor monotone also. So if f is a minor of G, then the tree width of f is at most the tree width of G, and similarly with tree depth. So by the Robertson-Seymour graph minor theorem, it's known that if I look at the class of all graphs with tree depth at most k, it's known that this is characterized by a finite set of excluded minors. Okay? Well, although this set is finite, it's known to be at least doubly exponential in k. So characterizing tree depth in terms of excluded minors is a complicated endeavor. And a question you could ask is, well, suppose I'm only interested in approximating tree depth. Is it possible that only constant many minors approximate this class for every k? And in particular, if you just look at the longest path in a graph G, which is the same as the largest path minor in the graph, then already you're getting an exponential approximation. So just the class of paths gives an exponential approximation to tree depth. Okay? But for our result, we're going to seek a polynomial approximation of this parameter. Before talking about the case of tree depth, let me mention that the very celebrated result of Chakuri and Chisholm proved this polynomial bounds on the grid minor theorem. So this was a very big result in graph minor theory from a few years ago. They show that every graph with tree width, at least k to some constant c, contains a k by k grid minor. Okay? And what this is showing is that if you look at the size of the largest grid minor in a graph G, this is giving a polynomial approximation to the tree width. So we have a nice, one parameter kind of approximation of tree width. Note that a corollary of this result is that in order to prove a lower bound on the AC0 circuit size, or just the unrestricted circuit size of the G subgraph isomorphism problem, in terms of tree width, it would suffice to prove a bound for all grids. Okay? So in joint work with Kenichi Kawarabayashi, we prove a sort of analogous theorem for tree depth. So you could call this a polynomial grid tree path minor theorem. Okay? And the result states that for every graph with tree depth k to some constant, must contain at least one of the following minors. So either a k by k grid, or a complete binary tree of height k, or a path of length 2 to the k. So now we have just 3 obstructions which give an approximation to the tree depth. Okay, so as a corollary, in order to prove in order to get our AC0 formula size lower bound of the form n to the tree depth to some epsilon, it suffices to prove lower bounds for these three problems. Okay, and that's what we do. The lower bound on the AC0 formula size of grids already comes from the circuit size lower bound in the joint work with Lee and Rasparov. The result for paths was proved in this previous work from 2014. And then the new ingredient on the circuit complexity side is showing that we also get a bound on the subgraph isomorphism problem with respect to complete binary trees. Okay? And so as a corollary, we get this result here. Okay. So finally, to make the connection between AC0 and first order logic, this is, okay, so this is well-known sort of fact that okay, if you look at the model checking problem for first order logic, so you're given a first order sentence phi, so the model checking problem is given a structure with, of size n, with universe 1 to n, is the structure a model of the sentence. You can solve this structure by AC0 circuits of size order n to the variable width of the formula. And you can solve it by AC0 formulas of size order n to the quantifier rank. And perhaps I should have mentioned earlier in the talk that quantifier rank is the maximum nesting depth of quantifiers in your formula. Okay, and the kind of descriptive complexity corollary of that result. So this is, you know, the equivalence between first order logic and AC0, or one direction of that equivalence that we use is that from lower bounds on AC0 circuit size, you get lower bounds on first order variable width. And lower bounds on AC0 formula size give lower bounds on first order quantifier rank. Okay. So using that connection, we get our main result. So let me just to state it again. The first order formula phi with quantifier rank k is preserved under homomorphisms on finite structures. Then it's equivalent on finite structures to an existential positive formula of quantifier rank at most polynomial in k. Okay, and the proof is via reduction to this lower bound. The reduction itself is which is in some sense the main result in the paper, is pretty simple. I'm not going to say anything about it. I should just mention that even without the new result in graph minor theory, just based on the existing lower bound for distance k connectivity, you would already get a exponential bound here. And one other thing which I found is if you go all the way back to the very first lower bound for distance k connectivity of ITI in '89, via this fairly simple reduction, you would already get a non-elementary upper bound. So it would give an alternative proof via circuit complexity of our result. And yeah, the last thing I wanted to mention is that so we also get a sort of qualitatively stronger version of this result in that we get something which applies even to non-uniform circuits. So here's another way of seeing what this result says. So that the class of homomorphism preserved graph properties that you can compute in AC0 is exactly equivalent to the class of graph properties that are definable in existential positive first order logic. So in particular, if you're just looking at the homomorphism preserved graph properties in the class AC0, then this is contained in a very small class, polynomial size monotone DNFs. So AC0 collapses all the way to this class with respect to this family of properties. And this is, stands in contrast to previous results which show that syntax and semantics are very different with respect to things like monotonicity. So Tiger-Ravitch showed that monotone AC0 is different than, syntactically monotone AC0 is different than semantically monotone AC0. Okay, so thanks. Yep.
Beautiful talk. Really enjoyed it, but it seems like the only parameter that you care about is the depth, the quantifier depth of the formula.
Yeah.
So what is this polynomial? I mean, it's a fixed polynomial, right?
Yeah. So
so what is it?
Yeah. So the polynomial comes from the it comes from this theorem here. It's related to this C here. So in our result, you can actually, I think you could say something like 5 from our. I mean, it should. It should be 1. I mean, I think there should be no blow up at all. Yeah, that's an artifact of the proof, probably. Okay, thanks.